In this lecture, I will provide you with some background on direct product spaces and how to deal with quantum mechanics for composite systems. If you are already confident about what you know about direct product spaces and composite systems, you may actually skip this lecture and go on to the next one. However, it may always be a good idea to brush up. Notice that the headline says a composite bipartite system on H1 cross O times H2. Now, bipartite is simply a fancy way of saying that our system has two parts, and the overall system is composed of these two parts. So let us call these two parts system A and system B. They have their own individual Hilbert spaces, set of all possible vectors or kets which describe states of A and B respectively, and we are calling them H1 and H2. Now, if Psi1 is a state in H1 and Psi2, the ket Psi2 is a state in H2, then the direct product state Psi1 O times Psi2 is a possible state of the composite system. Now, all that this particular state means is that the system A is in state Psi1 and system B is in state Psi2. So, in this case, we are sure of which state each individual part of the composite system is in. However, remember this is quantum mechanics, so superposition principle holds. So, a general state for the composite system may not be of the form Psi1 O times Psi2, where Psi1 is in H1 and Psi2 is in H2. By the way, I am using the term O times simply because that's the name of the LaTeX symbol which types the direct product symbol here for you. So instead of saying Psi1 direct product Psi2, I am just saying Psi1 O times Psi2. So a general state of the composite system will in general be a linear combination of such direct product states. And the set of all possible states of the composite system is what you call the direct product space H1 O times H2. You may have already come across this in a linear algebra course where a direct product of two vector spaces can be formed by taking all possible linear combinations of direct products of vectors, one taken from each vector space. Now, there are states in H1 plus H2 which cannot be written as a direct product of states in H1 and H2. And these states, these special states which cannot be written down as a direct product of individual states, are states for which you can no longer say for sure that the subsystem A is in such and such state and subsystem B is in such and such state. You can only talk about the state of the whole system. Such states are called entangled, and given current interest in quantum information theory, entangled states are a big craze. We are not going to talk too much about entangled states in these lectures, but I am pretty sure you have met them before in your last course, especially in the context of Bell's theory, inequalities and stuff like that. So what about a basis for this composite direct product space? Well, if Phi1, Phi2, etc. form basis of this vector space H1, the set of all states of subsystem A, and Chi1, Chi2, etc. form basis of H2, then how do you form basis of H1 cross H2? You take the direct product of any one of the states from the basis of H1 with the direct product with any one of the states from the basis of H2, and take all possible such direct products, and you get a basis for H1 O times H2. And it's easy to see that if H1 and H2 have dimensions m and n respectively, then there are mn such direct product states which form a basis, and so the direct product space H1 O times H2 has dimensions mn. Now what about operators? Well, you can have operators which act individually on A and B. You can take them and form direct product. So direct product operator would of the form A1 cross B2 or A1 O times B2, where A1 is an operator acting on H1, B2, well, the 1 and 2 here signify which space they act on. So A1 acts on H1 and B2 acts on H2. Then you can define the direct product operator A1 O times B1 O times B2 by its action on a direct product state. So what does A1 O times B2 do to the state Psi1 O times Psi2? The answer is simple. A1 gets to act on Psi1, B2 gets to act on Psi2, and the resulting output is a direct product of these two results. So it's pretty easy to remember actually. Each operator in the direct product acts on that particular piece of the composite state which is in its jurisdiction, which is under its jurisdiction, which it can act upon. So A1 acts on Psi1, B2 acts on Psi2, and you get a direct product of these two. Of course, the real concern would be that there are states which are not direct products of two states, one in H1, the other in H2. So what do you do for such entangled states? The answer is you just use the same definition by extending it using linearity. So if you have a state like C1 Psi1 cross Psi2 plus C2 Phi1 cross Phi2, you just figure out what A cross B does to Psi1 cross Psi2 first, then you figure out what it does to Phi1 cross Phi2, and linearly combine these two results to get the result of A1 cross B2 acting on the linear combination. Now, if you have two such operators, two such direct product operators, A1 cross B2, where A1 of course acts on H1, B2 acts on H2, another direct product operator, C1 cross D2, what is the product of these two operators? Remember, a product of operators essentially is a composition, one operator acting after another. So here, we know C1 cross D2 will act on a direct product state by C1 acting on the first piece, D2 acting on the second, and A1 cross B2 will act on that by A1 acting on the now first piece, which is actually C1 acting on the first piece. So A1 C1 acting on the very first piece, and B2 D2 acting on the second piece. So since this works for all direct product vectors, this is the result you actually get. It's again pretty easy to remember. Operators which act on the first space gets composed together, operators which act on the second space gets composed together. So this is the background that we are going to need. We are now going to talk about some examples of this in action using a very simple situation. Let's take two spin half systems, which were the subject of our last lecture, remember. These were two-dimensional systems spanned by 1, 0 and 0, 1, namely the kets half, half and half, minus half. And the basis vectors for the direct product space will of course be all possible direct products of these. So you take half, half with half, half, that's what I've called phi 1, 1. Phi 1, 2 will be half, half, just one state for the first spin, and half minus half the two state for the second spin. Similarly, we have phi 2, 1 and phi 2, 2. So 4 basis vectors in all. Very often, especially when we go on to study condensed matter physics, where these spins will have very important implications in magnetism, say, you denote half by a spin up, also in atomic physics of course, and half minus half by spin down. So these 4 states, phi 1, 1, phi 1, 2, etc. are often written as up, up, down, up, and down, down. We are not going to use this notation in this lecture any further. However, you might very often see this notation being used. Now, we usually choose these 4 basis vectors as an ordered basis of H1 direct product H2. Note the choice of the word usually. After all, you are fully free to choose some other basis if you want to. However, if H1 and H2 have a basis, of course they do have basis, the direct product vectors of those bases form a natural basis for H1 O times H2. And that's the one we are using here. Now, if we put them in this order, it's obvious that a general composite system can be represented by a linear combination of these states, and is represented by the column vector C11, C12, C21, C22 in that particular order. Of course, let's take a look at the basis vectors themselves. Phi 11 is a direct product of half-half cross half-half, which in the matrix representation is simply 1, 0 direct product with 1, 0. I've tried to use color coding here, so the red stands for the first spin, blue for the second. And notice that this is our very first basis vector for the composite system, and since it's the very first basis vector, its representation of the column vector is simply 1, 0, 0, 0. But notice that there is another way of looking at this. This is a trick which allows you to calculate direct products fast. Think of this 1, 0 as a two-component matrix, but multiply each of these 1 and 0 by the second column vector. So 1 times 1, 0 and 0 times 1, 0. Of course gives you 1, 0 here and 0, 0 here, which together form the 1, 0, 0, 0 basis vector. This is rather trivial, but this method gives us a quick way of finding out direct products of more complicated situations. Well, proceeding this way, we can easily see that phi 1, 2, which is 1, 0 for the 1 and 0, 1, the blue 0, 1 for the 2, which is of course our second basis vector 0, 1, 0, 0, and you can easily see that you would take the 1, 0 from this vector and multiply each element by the 0, 1. You end up with 0, 1, 0, 0, which is exactly what this is. So on for the other two. I will let you ponder about it yourself, but it's best that you just work it out on your own. Let us now go on to talk about operators on this particular composite system made out of two spin-half systems. Let us in particular consider the operator J1 plus. There is no real reason for picking on this particular one operator. Any other operator could have done, but this is just an example we are looking at. Of course, J1 plus is an operator which acts on H1 as evidenced by the 1 in the suffix here. And as such, the operator J1 plus does not really act on H1 cross H2, the composite or direct product vector space. So if we are talking about the operator J1 plus on the bipartite system H1 O times H2, what we really mean is a direct product operator. This is important. Very often the notation will hide this. In fact, we are going to often use notation which will hide this fact. But J1 plus alone is an illegitimate operator on H1 O times H2. What actually we mean when we write J1 plus is a direct product operator J1 plus O times I2, where I2 is the identity matrix or I2 is the identity operator acting on the second Hilbert space. So what we have here is real and genuine operator acting on the composite space is J1 plus on the first space, identity on the second. So what does J1 plus do to our first basis vector? Remember, J1 plus is really J1 plus O times I2, and our first basis vector really is 1, 0 direct product with 1, 0. 1, 0 of course for the first spin, 1, 0 again for the second spin. Both spins are up, so to speak. So as we have learned, the way in which the direct product operator acts is J1 plus will act on the first vector in the direct product, that is on 1, 0. I2 will act on the second 1, 0. And we will have to form the direct product of the results. Now what is J1 plus I1, 0? Well, remember 1, 0 is already the highest weight state, the state with the highest m value possible, half plus half. So the raising operator J1 plus acting on that actually kills the state. Because what I2 does on 1, 0 is that it simply leaves it as 1, 0. So J1 plus acting on 1, 0 is 0, 0, O times 1, 0. And that, of course, is nothing but the null vector. Of course, the null vector in this space, H1, O times H2. So it's a 4 by 1 column vector, which is 0 all over. Well, we can proceed in exactly the same way and find out J1 plus phi 1, 2 is 0 for the same reason basically. After all, when you say phi 1, 2, the first spin is in the state 1, 0 and J1 plus hitting that will give you 0. On the other hand, J1 plus acting on phi 2, 1 is simply H cross times phi 1, 1. This phi 2, 1, notice, is the first spin in the state 0, 1, the second spin in the state 1, 0. When J1 plus O times I2 hits that, J1 plus hits 0, 1, making it 1, 0, times H bar, of course, and I2 hitting 1, 0 gives you 1, 0. So what you are left with is basically 1, 0, O times 1, 0 times, and of course, an H bar, and 1, 0 times 1, 0 is phi 1, 1. Again, very simply, we can show that J1 plus acting on phi 2, 2 is phi 1, 2. Again, pretty easy to see. The phi 2, 2 is the state 2 O times the state 1. The state 2 acted upon by J1 plus becomes state 1. So now you have state 1 O times state 2. And the matrix for this can be easily written down by looking at J1 plus's action on the basis vectors. Remember, because J1 plus phi 1, 1 is just zeros, all zeros, this is a linear combination of phi 1, 1, phi 1, 2, phi 2, 1 and phi 2, 2 with coefficients all 0, and these coefficients go down the first column. So this column, I can't mark it properly here, it's just the first column is 0, 0, 0, 0. Similarly, the second column, which essentially belongs to what J1 plus does to phi 1, 2, is also all zeros. J1 plus phi 2, 1, the third column, will actually have an H cross in the phi 1, 1 position, so in the very first position. So if 1, 0, 0, 0 here, remember we have an H cross sitting outside. Similarly, since J1 plus acting on phi 2, 2 is phi 1, 2, on the fourth column you have a 1 sitting in the second position, the position corresponding to phi 1, 2. Just to show you that there is another way of obtaining the same 4 by 4 matrix, all you have to do is remember that J1 plus cross I2 is H bar 0, 1, that's J1 plus, the matrix representation of J1 plus. I2 of course has a matrix representation of 1, 0, 0, 1. And the way in which you can calculate the matrix elements for the direct product is simply treat the product as a 2 by 2 matrix essentially, where 0, 1, 0, 0 is sitting in the four corners. Multiply each one of them by the second matrix, that is 1, 0, 0, 1 here. Sorry, I messed up. I went back a bit. Now notice, this is what is happening. So 0, 1, 0, 0, the elements of the first matrix are sitting in the right position, and each element is multiplied by the 1, 0, 0, 1 matrix. Of course, this means that you're going to get 0, 0, 0, 0 here, here, here. Only this part is going to be 1, 0, 0, 1, which exactly is what J1 plus is, as we had worked out earlier. So the direct product gives you another easy way of directly calculating the matrix corresponding to a direct product operator, direct product of matrices, that is. Let's try one more just to make sure that we have understood this. If you take the operator J1 plus J2 minus, which again is not really an ordinary product, because ordinary products work only by successive action of J2 minus acting first and J1 plus acting next. But J2 minus and J1 plus actually acts on different vector spaces. So there's no way J1 plus is going to act on the result of J2 minus. So when we write this product, we actually are implying this. J1 plus direct producted with J2 minus. So J2 minus acts as on its own space, J1 plus acts on its own space. So this notation J1 plus J2 minus, which looks like an ordinary product, really stands for the direct product. Usually these things are obvious from the context, so you don't really have to worry too much about this notation. Very often we will drop the O time symbol simply because it makes writing easier. But you have to remember, when you have operators working on different spaces, then you cannot really have a product of such operators. All you can have is a direct product. So what does J1 plus J2 minus do on, say, phi to 1? I've just picked another basis vector to show you what happens. Of course, this is J1 plus direct product J2 minus acting on phi to 1 is 0, 1, direct product with 1, 0. 0, 1, that's a 2. And the 1 here stands for 1, 0. So J1 plus acts on 0, 1. And J2 minus gets to act on 1, 0. And we all know what happens. J1 plus raises 0, 1 to 1, 0. And J2 minus lowers 1, 0 to 0, 1. And this is all you get, with extra factors for H cross, of course. And so the result is H cross square. And the direct product can be easily formed. Remember, is 1 times 0, 1 and 0 times 0, 1. So you get 0, 1, 0, 0. Okay, so there was one more thing written there which I've just managed to drop out. That was H cross square ket phi 1, 2. And we proceed similarly to find out the matrix for J1 plus J2 minus. It's just easy to see that there is only one of the basis vectors here, namely phi 2, 1, the one we had picked, which gives you a non-zero result. All others give you a result of 0. So all 3 out of the 4 columns of this square matrix, 3 are 0. The only one which is non-zero is this one, which is 0, 1, 0, 0. You can check for yourself that if you took the direct of the matrices for J1 plus, which is 0, 1, 0, 0, and J2 minus, which is 0, 0, 1, 0, and form the direct product of matrices using the rule we just outlined before, you will get this result.